So what I'm going to talk about, I'm going to start by motivating the topic, by talking a little bit about what dark matter and dark energy are, or what they are not, and how they are related to the science of cosmology. So how we can use, how the content of the universe really affects what we know about the evolution of the universe. And then I'll talk about, well, my favorite way of trying to answer this question, which is gravitational lensing. So I'll talk a little bit about how gravitational lensing comes about. And in particular, I'll talk about the phenomenon of weak gravitational lensing and the mathematics that go behind actually using this as a tool for measuring quantities. And then, depending on how much time I have, I'll talk a little bit about what's going to happen. Okay, let me start with a rather obvious one, is that when you look out at the telescope, you see light. Now that could be light from emission. It could be light that's scattered, so reflections. Or it could even be cases where you see the lack of light, so you see absorption. And so, for example, the previous talks involving spectroscopy have all used the fact that you detect light and you find out things about distant objects and the contents of the universe from light. But of course, we also know that there are other ways of figuring out what's out there, and one of them is a dynamical way. Mass contributes to the curvature of space. That's what general relativity is. So one of the things that can happen is that gravity can reveal the presence of stuff that doesn't shine. For example, people who've studied the rotation velocities of galaxies have long known, at least for the last 40 years or so, that the orbital speed of stars and galaxies is much higher than one expects for the amount of stars that are visible. And if you do an accounting, not just of this, but of other things, what you find is that there's about 5 times as much mass as can be accounted for by all the normal matter that we know can exist. And this discrepancy of about a factor of 5 is what's now known as the dark matter. It's stuff that we don't see, and we have evidence that it's actually not normal matter, but in general, it's stuff that we can't see, and that we find evidence for from dynamics or from gravity. The properties of it is the mean density of this stuff is quite low. It's about 10 to the minus 27 kilograms per cubic meter. We know something about other properties of the dark matter. We actually know something about its pressure. We know that its pressure is much less than its density times c squared. In cosmologist terms, the ratio of the pressure to the energy density is sometimes called W, and W for this matter is pretty close to 0. This is true for most matter. If you think about the pressures related to the velocity, so the pressure is v squared, and for non-relativistic objects, v squared is much less than c squared. So this is always the case for normal matter. Because it doesn't emit a lot of light, it must have a very weak reaction cross-section with normal matter. Because otherwise, you would have phenomena which would lead to the production of photons by the weak interaction. And we know that it bumps into galaxies because we see it in galaxies and clusters of galaxies. And probably on smaller scales, but we don't know that for sure. So now comes the embarrassing part from the point of view of a physicist, is, well, what else do we know about this dark matter? The answer is we don't know anything else about the dark matter. In particular, we have no idea what this thing is. But that's actually not as bad as it seems. Once you actually figure out what we know about the physics of particles, you find out that there are lots of things that we know must exist, but we've never seen. And in particular, all the attempts to unify the forces beyond the standard model, the description of matter in terms of generations of quarks and leptons, predict the existence of particles. And the best model, or the best candidate for the dark matter, comes from an extension of the standard model of physics that we know on low energy scales called supersymmetry. And this is something that can actually be experimentally verified. There are projects, one of them actually at Brown, involved for looking for these particles in in deep underground caves, but there are also experiments at the modern colliders that are going to try to look at these things. So it's not completely out of the question that these things will be found. Okay, well that's embarrassing enough. In the last decade, things have gotten only more embarrassing. because we also know that the universe contains a lot of dark energy. And dark energy, in fact, it contains about 3 times as much dark energy as dark matter. Dark energy is different from dark matter because it's a substance whose pressure is actually different in sign. It's a negative pressure. Now, something that has a negative pressure is kind of hard to envision, but examples of this could be, well, what comes out of Einstein's equation as a cosmological constant, or if you imagine that the vacuum, empty space, has a non-zero energy, energy density, then that gives you something with a negative pressure. And it turns out that in generic models of particle physics, you can have particles represented by scalar fields, and in the limit where the potential term of the Hamiltonian dominates over all the kinetic terms, those things also behave. Negative pressure. Okay, what makes a negative pressure fluid interesting? Well, in normal life, we think of gravity. You know, when we drop something, it falls to the ground. Gravity is an attractive force. And we usually think of gravity as being generated by the mass of an object. But actually, in general relativity, what actually matters is the stress-energy density. One component of which is the energy density. And for normal matter, or for dark matter for that matter, that's the dominant component. Because the pressure terms are small, you can just ignore it. But something with a negative pressure, in fact, as long as the pressure is less than minus rho over 3, actually changes the sign of the gravitational effect. So you built yourself something which has a repulsive gravitational effect. And that's kind of weird. That's different from what we have experienced. Nevertheless, one of the things we've discovered in the last decade by studying at, in this case, distant supernovae, is that the universe itself appears to be pushing itself apart. So the universe's expansion is accelerating. Now, if you have a universe that's filled with dark matter, or for that matter, a universe that's filled with normal atoms, that's not going to happen. Because normal matter has an attractive gravitation. It slows the expansion. It's only something with a negative pressure that causes acceleration. Okay, so we have 2 large sections of the description of the contents of the universe that do very different things and whose physical description we don't understand. And I wanted to belabor the point a little bit, just to go over why the content matters. I said that the expansion of the universe is controlled by the contents. And in general, if A is the scale factor of the universe, which measures the size of the universe, you can write expressions for the second and first derivatives of the scale factor as a function of the density and the pressure. And what you find is that as long as the energy density, or the density, is greater than the pressure, or that the pressure is positive, then you end up with a deceleration. You can only get an acceleration if this term dominates over this term, and this term is negative. But it turns out that structure also affects the contents of the universe in a different way. When we look out at the universe, we see that there are lots of stars and galaxies and planets and people. But when we look back at the history of the universe, we find that back in the early universe, the universe was actually rather homogeneous. So there weren't large sections where you could make a big difference between a person and not a person, or a planet and not a planet. That structure grew by gravitational collapse. And the growth of structure is also determined by the density and by the expansion rate of the universe, which depends on the density and depends on the second derivative. So the contents in terms of dark matter and dark energy actually control not just how the size of the universe grows, which is an interesting point itself, but how we, and by extension everything else, came to form out of this primordial, nearly uniform. And then there's a last tiny bit of curiosity. It's kind of galling to know that 96% of the universe is stuff we know nothing about. Okay. So just to say, repeat it in words, you can write the effect on the expansion of the universe as an evolution of the Hubble constant. You've heard of the Hubble constant. It's named after Edwin Hubble from the telescope was named. The Hubble constant is not a constant. It measures the time evolution of the expansion of the universe. And you can also measure the growth of structure. And you can measure the growth of structure analytically if you can describe starting with a small perturbation, because you know in perturbation theory how to solve for small perturbations how they would grow. It turns out after they become big, then you're essentially solving an n-body gravitational problem, and that doesn't have a general exact solution, so you do it numerically. And so in general, when you're trying to compare the development of structures in cosmology, then you're trying to use them as a test of the amount of matter. Here, this is the density of dark matter, and this is the density of dark energy, and the parameter omega just measures the ratio of that to some number, which is the critical density. But the relative numbers of these just measures the relative densities. The problem is that the clustering is highly nonlinear, so you end up using numerical simulations. And numerical simulations are very good at following gravity. People know how to calculate the gravitational attraction between particles of gas or particles of dark matter. They're really bad at figuring out what galaxies are. Because galaxies are complicated things. They have stars in them, they have gas in them. The amount of light you get from a galaxy depends on not just how much stuff is there, but how it's formed stars, where it's formed stars, does it have dust, does it not have dust. As a result of that, what the simulations really give you, what these wonderful pictures of the growth of structure give you, is a map of where the mass is. To compare that, to make an estimate of the dark matter and dark energy content, you need something that maps the mass. And that's why, for example, mapping the distribution of galaxies is a little bit hard to relate to the distribution of mass. Because you don't know whether the galaxies are positioned always where there's mass. What if there's a lump of dark matter with no galaxy? That's not counted in this system. But if you have a way that's sensitive to mass, then you can make a direct comparison. So that's my leading argument as to why one might want to measure this by gravitational lensing. Okay, so let me just spend a few minutes talking about what gravitational lensing is. Gravitational lensing is basically makes use of the fact that, as general relativity states, the presence of matter changes the local curvature of space. So near matter, space is curved differently, and light, which travels on null geodesics in this space, is going to change its path. You can think of it in sort of a layman's term as saying the presence of matter changes the definition of what a straight line is, and light is going to travel in its own straight line. By changing the definition, it turns out that the path of light, instead of being straight from the source to you, ends up curving. Now, the deflection is quite small. If you sent a ray of light grazing on the surface on the edge of the sun, it would bend by about 1 second of arc. But nevertheless, it is measurable. So just to give you a schematic of what happens in gravitational lensing, if you have no gravitational lensing, then the light is just going to travel from some distant star to you in a straight line. And so when you look back at that distant star, you'll be looking straight at the direction of the star. If you put some large source of mass, let's say a galaxy, between you and the star, then the path of the light will be different. The path of the light will be curved around the star. And I apologize for this being white. I just realized that's not going to show up so well. But, so what you notice is that the light rays coming to you around both sides of the galaxy are converging to you. That'll be a hint as to why something will be called the convergence later. However, when you look back out at the object, you're looking opposite to the direction in which the light beams go. And so the effect is that the images of the objects diverge and move away from their true position. In particular, they move away from the line of sight of the star. So the images will appear to scatter away from any source of mass. So that's important. And so in this particular case, because there are two separate beams from this source which make it to you, you end up with two separate images of the source. This is what's known as strong gravitational lensing. Okay, I just want to give you a little bit of the flavor of the basic relations. If you want to calculate the apparent angle at which a source is seen relative to the lensing mass compared to the initial angle, you basically end up with something that looks like the lens equation, a very trivial equation, at least in flat space. In curved space, it's a little bit nastier, but still can be written the same way. And the deflection turns out to be generated by a deflection potential, which is related to the mass by essentially Poisson's equation. And this quantity k is called the convergence, and it's related to the masses. It tells you how much the light rays will bend in. That's why it's a convergence parameter. But remember, when you're looking back, you should think of it as a divergence parameter. It tells you how much the light rays are perceived to shift out. And in general, this is scaled to some quantity which depends on the distances, because like any lens, it's got a focus. So depending on how far behind or in front of this bending object the light source is, you'll change the values. And that would be critical because this part will encode information about the scale of the universe. By the way, if anything's not at all clear, you can try. Okay, so just to give you a more definite breakdown of what's going on, the deflection is what you observe, that is how much the shift is observed. It'll turn out that in the particular application of weak lensing, you actually only measure the gradient of this. But that depends on the amount of mass, that's what controls the amount of bending of the light, or the curvature of space, and the geometric factor. And both these things are measures of cosmology. That's one of the things that makes gravitational lensing strong. It tells you not just how the mass structures are formed, but also how the volume of space behind them is changing. And it turns out those two things are separable. Okay. Just going to give you one other basic bit of notation. It's true that the convergence is important. If you imagine shifting an image that's not infinitely small, but finite in size out, the divergence of the light rays will cause the apparent size of that object to change. The convergence basically measures the magnification, the isotropic part of the image, how the image grows. But you can also define another parameter, which is the shear, which is the traceless part of the Hessian, which is basically measuring the deformation. How is the object changed in shape? And the shear acts to deform a circular object into an ellipse. And if you think about it, there are two independent ways of twisting something. You can twist something along one direction versus another, or in the 45-degree direction. And the reason you get this 45-degree issue is that if you take an ellipse and rotate it by pi, you get the same ellipse value. So the thing is invariant in rotation by pi instead of 2 pi. And that's why a pi over 4 rotation gives you an independent. You can either think of this as two independent components, and a lot of people do, or if you like complex numbers, you can think of it as a complex number, or you can think of it as something with a magnitude and an orientation. Those are all equivalent ways of describing the shear. Okay, the important thing is that both the shear and the convergence, which I remember is related to the mass, are given by second derivatives of this deflection potential. And that means that there is an integral relation that's going to connect those two. It means that if you know the shear, you know something about the convergence, and vice versa. Okay. It turns out the convergence is something that's fiendishly hard to measure. People have proposed ways of measuring this magnification effect, which basically amount to measuring how much brighter the object is. That turns out to be hard because in astronomical situations, you can't go and remove the lens and say, oh yeah, that's how bright the thing really was. So you're stuck by trying to infer the apparent brightness from some other knowledge about types of systems. The shear turns out to be something that's measurable. Okay, let me just give you a little bit more background. If you go back to the lens equation, it turns out that the number of real solutions to the lens equation tells you something about the multiplicity of things. In the case where there are multiple real solutions to the lens equation, what happens is you end up with multiple imaging. And in multiple imaging, you end up with an over-constrained problem. So you can actually reconstruct the true position of the source and actually measure the deflection. That is, how much the light ray has been shifted. In the general case, where you only have one image, because you can't remove the lens, you're still stuck, because you can't tell, oh yeah, that's where the star really was, or that's where the galaxy really was. That's why you have to use the shear to tell you something. Because in this case of the shear, there's only one image, so you don't have the unlensed position. But the shift in the position is going to shift. As I said, it shifts away from the source of the mass. If you have an extended object, both corners of the object are going to be shifted away from the mass. And if you have an extended circular object, it's going to be turned into an ellipse. So the fact that the stretching is tangential, well, the object does appear at a different location, but that's unmeasurable. But the object is stretched tangentially, and that's the key part. That's going to tell you what the gravitational effect is. And if all galaxies and all distant objects were little spheres, we'd be done. Life isn't, depending on your point of view, life is either more interesting or more frustrating than that. If you look out in the universe, objects aren't round. Yes, some galaxies are essentially round in shape, but then there are some objects that definitely aren't round. But one of the key aspects of this is that if you describe these as ellipses, and approximate the shapes of objects as ellipses, what this means is that the ellipticity isn't a well-defined quantity. But the orientation of the ellipse, if you think of it as a magnitude and orientation, is a random number. There is no reason for all the galaxies to line up this way with respect to us. And in fact, if you go out and measure it, in general, there's a random distribution. But around the source of mass, the ellipticity orientations aren't random, because the deflection is always radially away from the source of the mass. And so the net effect is that you build up an excess probability of ellipticity in the direction tangential to the line of sight, connecting you to where the mass is. Okay, so what we do is we actually approximate each source with a position angle and a scalar ellipticity, where you can build either a complex or a tensor ellipticity out of the ellipticity and orientation. And then, by taking the tangential component of ellipticity, where here, for example, an object stretched like this would have a high tangential ellipticity and a zero cross ellipticity, 45 degrees, where something this way would have cross ellipticity but no tangential ellipticity. And someone here would have a negative tangential ellipticity. You can decompose the ellipticity into two components. One of the components is what the gravitational lensing signal generates. So if you measure the expectation value of the tangential ellipticity, you get some measurement of the mass. In general, the second component is not something that gravitational lensing generates. And that turns out to be experimentally quite useful, because if you know that something should have zero signal, you can test to see whether you see a signal in that channel. And by measuring the expectation value of this, any deviation from zero tells you the extent to which your experiment has systematic uncertainty. Things like, your telescope didn't really track the sky, so all your images are blurred. That will generate a signal. But it will generate a signal here too. Okay? In general, you can recast the integral equation I wrote previously for kappa into the function of the tangential ellipticity, because the tangential ellipticity is a measure of the shear. Right? The shear told you how elliptical the source was. The direction of ellipticity is the tangential direction. So the measurement of the tangential ellipticity of a galaxy is a measure of the shear, which can be used to solve for the density. Now, it turns out that there are a couple of catches. Because you don't have an infinite distribution of galaxies, you don't have a galaxy everywhere in space, you're not really solving an integral. You have to turn that into a finite sum, but that's fine. But there's a second issue, which is if you look at the denominator of this, there's a problem with this at position x prime equals x. Right? There's a pole there. And it turns out that this gives you a problem if you happen to be estimating the ellipticity of an object that's right on top of the mass. Because that's an undefined problem, right? It should be deflected away from it. So any amount of mass there should deflect it. And so any amount of kappa should yield for the infinite tangential ellipticity of that. For that reason, we typically actually calculate something that is not kappa, but kappa-like, which is involved with a weight function, which de-weights, so basically removes off the weight from objects that are right on top of the weight you're testing. And it turns out there's a second issue with objects very far away. In theory, this sum is over all galaxies. It's a pain to take an image of the entire sky. So you have to truncate your sum. So with these caveats, what you're doing is reconstructing the amount of the mass. But keep in mind that that's going to make what you reconstruct not quite the mass. just to show you that you're not only interested in reconstructing the mass, once you've found a mass, what you can do is change your background objects. So if you consider two galaxies, one of which is further away behind the same mass, the amount of deflection, this delta theta, is going to depend on the ratio of distances for the same mass. And in this way, you can separate out the amount of growth of structure, which you calculated by that reconstruction of kappa, and the volume of the universe using the same observations. So that gives you two tests of the cosmological parameter for the price of one. A good deal. Okay. So how do you actually apply this data? Well, remember, because galaxies were randomly oriented, any individual galaxy has its own random component orientation. And that means you need to sample a lot of objects behind the mass, because you need to beat down this random orientation and use the fact that the average orientation is zero. The average orientation is random. Luckily, galaxies are big and bright, and there are many of them. And that means you can, if you take an image of the sky, you will find a lot of them. The current estimate of number of visible galaxies is about 50 billion within the observable universe. That's a cheating estimate. That's the number of galaxies that people have seen down to that brightness. The actual number of galaxies is probably a factor of 100 larger if you count the smallest galaxies. So you need to sample a lot of galaxies at each location to remove the random effect. And if you have distance estimates of galaxies, that allows you to do this second test of measuring as a function of distance this year. Okay. So if you want to try to go out and experimentally determine this, you need a deep imaging survey. That means you need to detect faint things which are far away. You actually need to measure the shapes of the galaxies. Remember, if you can't measure the ellipticity, that doesn't help. And you need to detect many masses. Well, the definition of a survey is you can't study one object on a survey. So let's talk about a project that I've been working on. It's called the Deep Lens Survey, with not very imaginative names. It's a deep survey for lens. It was approved as a 5-year, it's now actually a 6.5-year survey program, which means that the U.S. National Observatories gave us a chunk of time every year to do these observations, so we can be sure of completing the project. And the idea is we take 7 patches of the sky and figure out, well, what is there in 2 dimensions and 3 dimensions. The exposure times, the detector we use is at its heart similar to the digital camera that's in your camera, except that, of course, we've got a huge objective lens in front of it, which is a 5-meter mirror, and our exposure times are typically about 5 hours. So, very slow digital cameras probably. Well, we divided our observations between the 2 telescopes in the north and the south. This is Kitt Peak in Arizona and Cerro Colombo in Chile. And through February 2006, we were given about 143 nights, several of which were cloudy nights, no fun at observatories. And we've almost completed our survey. The last official nights for the survey were October 23rd, 2005. We have 3% of this field to do, so we'll probably get half a night sometime this year to finish it. Just a little bit of an aside, why we actually want to use these 2 telescopes. Well, one of the reasons we want to use them is that the 2 telescopes are about the same. And that's useful because we don't end up having problems with our detectors being different and having systematic from that. The telescopes are at plus 30 and minus 30 latitude, so they allow you to see both hemispheres. So we can look sometimes in the northern hemisphere, sometimes in the southern hemisphere, not worry about some weird systematic having to do that. And there's a second kind of bizarre reason. These telescopes were built a while ago. They're actually not the newest and greatest telescopes. And that's good for us, because when they were built, the technology for detection were photographic plates. And if you've ever seen historical photographic plates, they were big numbers. And so the telescopes were built with fields of view. In the 1980s and 1990s, CCD technology, the same digital detectors that are in your cameras, started taking over because they were much more sensitive to photography. But at the time, they couldn't build very big detectors. And so when they built these huge 10-meter telescopes, they built them with itty-bitty fields of view because, well, they'd never get enough detector space to fill the big fields of view with the big telescopes. Well, things have gotten cheaper. Now we have big format digital detectors, which aren't that useful on those big telescopes because the fields of view. It's the older 4-meter telescopes, which are the older technology, that are ideally suited for the newest detectors, at least until the next generation of telescopes get good. And the thing that makes this telescope, of course, work is that now we have big digital cameras, so our digital camera lives in here, it's sort of person size. By comparison, just to give you a sense, this is person size here, this is where the mirror lives, and you get a detector that looks something like this. To show you who the collaborators are, we've got a lot of people. It started as a collaboration between myself and Tony Tyson, who was at Bell Labs. That group all went to Davis, except Prof went off to Google, so we have spread out in the diaspora. What we're trying to do? Well, we're trying to figure out where clusters are, to figure out where the stuff is. And we're also trying to figure out things like the sphere correlation function, and some things that I don't have time to talk about. Just to give you a sense of what the data looks like, this is 1.6% of the survey, and it highlights a generic problem I have in this lab, which is that the resolution of any projector I have is much too small to show you the data. So this is 0.5% of that 1.6% of that data. And it's not quite at the right resolution, but it's starting to get there. These little dots here are the things whose shapes we're measuring. So there are about 30 million of them in the previous picture. It's a bit of a computational challenge to measure the shapes of them, but computers are there for a reason. And you can do neat things with this. You can make a comparison between what you see. This is a map of 2 degrees of the sky by 2 degrees. This is about the full moon would fit sort of in here. It's a little bit of a misleading map because all the bright things you see, or almost all the bright things you see, are stars in our own galaxy. They're just 400 clocks. Thanks for this question. Thankfully, but of course, that's contrast to what is there. If you ask what is the gravitational lensing signal, what you see is not the stars, but where the galaxy, where the mass is. And if you look kind of carefully, you'll see there's this condensation of yellowish things right here. That's a cluster of distant galaxies. It's actually 2 clusters of distant galaxies. And there they are. So you actually do detect the mass distribution. What we're doing now is measuring the distances to these clusters and trying to reconstruct where the clusters are on the moon side. That measures the growth of structure. That's one of the 2 cosmological measures. Just to keep in mind, in that map, each of these peaks corresponds to about 10 to the 14 stars worth of mass. So it's a large amount of mass. Why is it important? Well, if you measure the growth of clustering, that gives you the direct comparison with the cosmological simulation. People who simulate the growth of structure can stop their simulations at any point in time and tell you, well, how many clusters have you formed at that time? How much mass is there? Comparing that to observations tells you, gives you a test of, did that simulation with that type of cosmology match your observations? And you can reconstruct them. And it turns out that the simulations are quite sensitive. Here are 2 separate models with dark energy, but with different types of dark energy. One is a scalar field-driven dark energy. One is a cosmological constant-driven dark energy. And these are contour plots of the number density of clusters as a function of redshifts compared to their mass. So the highest mass clusters are over here. And you see 2 effects. One is, as you look further back in space, you're looking out at a larger and larger cone. That means you're encompassing a larger volume. So rare clusters, you get more and more of them. But at some point, the large clusters stop forming. So if you look further and further back, yes, you're looking at a larger volume, but there are fewer of them. So the number density drops. How that grows and shrinks depends on the growth of the clusters. So this becomes a test of the growth of the clusters. So the first result from the Deep Lens survey is that we have a distribution number density, which tells us that the equation of state is actually closer to a cosmological constant. It's less than minus 0.7 to 2 sigma. It's consistent with minus 1, which turns out to be the cosmological constant. It's consistent with the cosmological constant, but it turns out that this particular survey is not good enough to rule out all other scalar field dynamics. So what's next? Well, we've pretty much exhausted the effect of the Deep Lens survey. This is a plot made 5 years ago when we actually planned to do a bit more, and charitably call this completed. But there are surveys on the books in the next few years that will extend this from tens of square degrees to 1,000 square degrees. Not going to quite as great a distance, so there's some trade-off there. But the next big jump comes up here, where the numbers of square degrees goes to thousands and thousands of square degrees. To give you a sense, once you get to 20,000 square degrees, you're seeing essentially the entire sky. So let me describe those machines in a couple minutes. If you want to go out and measure a large area survey, you need a telescope that does a lot of things. You need a telescope that measures an object with a given signal to a given signal-to-noise ratio. So that's what you want. And to make it efficient, you need that object to collect a lot of light. So you need a large collecting area in your telescope. You need a large field of view, because you want to get a lot of the sky at a time. You need to detect a high fraction of the photons you collect. And you actually need the telescope to be working a lot. It doesn't do you much good if you're in Providence, where it swims a lot, tell you a lot. Even if you have the biggest telescope in the world, it would not actually be the most efficient site. And then you need to also pick a site which is dark, so you don't get a lot of noise from the sky, and which has good image resolution. So there are two ways of doing this. One way, you can really work on your site. The site with the best resolution and the darkest sky is nowhere on Earth. It's in space. If you get out of the Earth's atmosphere, you get no blurring from the Earth's atmosphere. And you can actually move yourself far enough away from the Earth and point directly away from the sun, so you get essentially zero light. You get a little bit of infrared light from the backscattered dust. So the techniques that go into space work really hard at minimizing this. At the cost of this, because it's really expensive to launch a big thing in space. So you tend to build smaller telescopes, but in darker sites. On Earth, you can build bigger structures, because it's cheaper. You can actually drive a truck to your construction site. Trucks are much, much cheaper than shuttles. On the other hand, you're stuck behind an atmosphere. So you're building up this at the expense of this. And both techniques are being used. So just to give you a sense of what's being done, from the ground we're building a project called the LSST, the Large-Scale Synoptic Survey Telescope. It's a telescope that's 8 meters primary collecting area with 10 square degrees of field of view. So in other words, 400 full moons worth every time the shutter closed. With a nice camera, it's a 10 gigapixel camera. Use your megapixel camera. With a 5-second readout, with the idea that every 20 seconds the camera opens and closes. And the idea is that with a telescope like this, you can image the sky, well, actually half the sky, right? The stuff behind you you can't see, every 2 weeks to rather faint magnitude. So about a little bit brighter than the deep month survey did in 5 hours. But that entire sky. And then you just keep doing it. Time after time after time to build up very, very deep images of the sky. This turns out to be a major data handling issue, because if you're reading out a 10 gigapixel camera every 20 seconds, every night, the amount of data that you store turns out to be in the petabytes. That's hard to deal with. The closest analogy is the particle accelerators, where they're smashing so many atoms that they actually get enough collisions to form a petabyte. There, they can use some interesting bits of quantum mechanics that says that electrons are all the same, so any reaction that gives you an electron is equivalent to any other. And they throw away most of their data, because they're learning no new physics from it. Galaxies aren't electrons, so we can't throw away any of the data. We haven't yet figured out what we're going to do with all the data. I want to emphasize this is a huge project. There's tons of universities that are partners, both Google and Microsoft, for unknown reasons, have decided to join it. Well, data mining issues, I guess. It's a private public funding model. There's about 30 million of private funding that's been built. It was given about 50 million of NSF funds. But its actually estimated cost is about 200 million. So it's still a long way from being built. Okay, I want to... Oh, and the idea is, the thing that makes this hard is the camera. The previous slide, the camera part inside was only about 2 feet across. Here, your actual camera is about 5 feet across. And you have to have 4-foot wide filters in front of the camera to take images. So exactly how that's going to be built, I'm not sure. But it should measure the dark matter and dark energy values to very high precision, and in fact tell you whether W, which is this measure of is it cosmological constant or not, to plus or minus 0.1. That's 3 times the precision. Okay, the other mission is from space. There's a NASA DOE joint project called the Joint Dark Energy Mission, which for which 3 proposals are due in March. So if you're interested in sending a proposal next month, well, and I'm participating in one of them with the rather unpleasant, rather unfortunately chosen acronym of JEDI. And the idea behind this is that in space you build a small telescope, but the images are much less noticeable. So the idea behind JEDI is that you build yourself a 2-meter telescope, and you go off and look at supernovae spectrum, recleansing, that's the thing with it. And that has a large number of co-eyes for reflection process as well. Many of them in the mass. Okay, I would be remiss if I didn't give you some sense of the timeline. Because of funding issues, LSST is slated for 2012. Really, 2014 is when you can expect to see anything happen there. Right now, they're still deciding where to put the thing. There are 2 candidate sites. One just south of the U.S.-Mexican border in Baja California, which turns out to be a very nice site, but not very well developed, because that part of Baja doesn't have any nice resorts near it, so you have to actually build a road there. And the other part is in central Chile, where lots of other telescopes have been built, so the site is well developed, but it's not quite as good a site. So they're still trying to wrangle the cost versus implementation. JDAM suffers from a bigger problem. JDAM is funded largely by NASA, and that's a state of somewhat chaos since it's trying to implement 3 missions at once with 0 budget, so implement all of them. And so, right now, it's in limbo based on space rarity. What they're going to do is fund development work at a couple $1 million a year, but when this actually gets to fly, is anybody's guess. My guess is it's going to be after this. Until now, if you went back to the table of what's going to be done, you will find that the number of square degrees won't grow until you get to about 20,000 AD. So for the next 3 or 4 years, this is about the best we can do. And it's only in the next decade that we'll really solve the problem of where the dark matter is, what the dark matter is. Okay, I'll stop there.
This is kind of a strange question. So the whole existence of dark matter always seems to me vaguely like the existence of ether, and that we have very little evidence for it, and we're trying to find it if we can.
Well, I didn't calculate that. Dark matter, the existence of dark matter comes primarily through gravitational measurement. But it is true that dark matter has been measured by gravitational measurements in many different places on many different scales. And people have tried to come up with alternate models. In fact, there are many, many alternate models for saying, well, there really isn't dark matter. What this is showing us is some change in the laws of physics. This is sort of the equivalent of ether versus relativity. And all of those models have failed to characterize the distribution of gravitational forces as a function of scale. So they tend to work on certain scales and not work on other scales. To make those models work ends up giving you something which has multiple tunable scales. And that starts looking like epicycles. So you have this trade-off between ether and epicycles. And generally people have tended towards the ether part than the epicycle. But yes, the fact that we haven't detected dark matter makes it a little suspicious. The thing that makes me not quite so nervous about it is that I know that the standard model is incomplete. And I know that there's physics behind the standard model. There has to be something because there are questions, for example, like the distribution of masses. The standard model is part of an answer. The expansions of the standard model that theorists have come up with naturally include particles which are dark matter. So in particular, there's the thing that the LHC, the CERN collider was built to detect is the Higgs particle. And the Higgs particle, most of the generations of the Higgs particle include through the Higgs a family of other particles. So if this supersymmetry theory is true, there's this other family of particles, one of which is going to be the lightest one. So all the more massive ones can decay to the lightest one. The lightest one is stuck. And if its mass is 0, that's your dark. If it's not from the Higgs phenomenon, we have many orders of magnitude in energy to get to the next unification scale, where there are particles where there are particles at mass scales that are unreachable right now, so that we can't test them in collider theory, but they've got to exist. And those could be the dark. So we haven't exhausted the corners to look for the dark. And that's why I'm not quite as nervous about it. It's true that if all we had was a gravitational effect and no plausible candidate, then I'd be nervous. But the fact is that we have plausible candidates, and so it makes sense to me that it could be otherwise. The dark energy is a little bit messier from that point of view.
Does the theory that you're talking about that predicts these particles, which have been found yet, also predict they will not interact with ordinary matter?
Yeah, so in supersymmetry, they interact with ordinary matter only by the Higgs. And the Higgs is very massive, so at low energies, the interaction loss actually is low.
So it's consistent with...
That's right. But not zero. Right? So the idea is that if supersymmetry is right, there is some finite, if very small, cross-section for it.
And it's consistent with the fact we have...
But it's consistent with the rates at which you start pulling them out are, if you take a kilogram of matter and you don't see anything for a few thousand years, then you start working. But we haven't done that for a few thousand years. Yeah.
You mentioned a mean density of dark matter. How do you know that?
So the mean density of the dark matter is calculated in a bunch of ways. One of them is to take a patch of the universe, for example, the one we mentioned with lensing, and ask how many clusters there are and how much volume they do. So it's a mean in the average sense. The second is related to this question of the evolution of the size of the universe. Remember, the scale factor of the universe depends on that mean density. I didn't stress where those equations came from, but those equations are equations describing the evolution of the universe on large scales, where you can use this average density as a representative density. On small scales, the universe doesn't behave this way. But by measuring the evolution of the universe, I will get there. So by measuring these side of the equations, you can actually measure. So both those ways you can use. You can compare that to the distribution of normal matter, which is a factor of 5 to 6 lower. And it's a matter of the whole talk to figure out what we know about the distribution of normal matter.
Okay, let's think. That's the Dell'Antonio.